So let me introduce Dr. Teixeira before she takes over the podium. Dr. Teixeira is a professor of civil engineering at the Federal University of Espirito Santo, Brazil. Her research focuses on infrastructure materials characterization, including rheological, chemical, physical, and mechanical laboratory experimentation, as well as computational modeling of composite materials based on microstructural multi-scale models, viscoelasticity, and fractal mechanics. Since she obtained her PhD in 2011 from here, UNL, she's a UNL grad, as you know, under me. She has been involved in projects sponsored by Brazilian funding agencies and industry sectors. She's a member of Binder Performance Test Group of Brazilian Association of Technical Standards. She has received national recognition from Brazilian governmental agencies such as CMPQ. She's Brazil NSF. Yeah. Research Productivity Scholarship and CAPES Scholarship grants for the improvement of higher education personnel. She continuously works on regional, national, international technical committees and on editorial services in the field of materials and civil engineering infrastructure systems. So I'm very happy to have her today. She's actually departing here next Tuesday.
Right.
So it's the right perfect time, right?
Perfect.
To wrap up her visit and then presentation for us today. So please welcome Dr. Teixeira.
Thank you, Dr. Kim. For me, it's an honor being introduced by my former advisor and many of you that is right now passing from what I passed 8 years ago when I finished my PhD under Dr. Kim. We'll have the same feeling, I'm pretty sure, in the near future when you graduate and become professionals. So thank you a lot, Dr. Kim, for once again receive me here at UNL. UNL for me is like home. So I've come back to this very place that I was here as a graduate student some time ago. So for today's presentation, I'm gonna present not only things that I did here this time that I was a visiting scholar from April 2018 to now, but also I would like to give you a little brief, talk a little bit about what I do in Brazil, some of recent projects that I'm working on, and how those projects could be correlated with things that I accomplished here during this time at UNL. But before I start, I will start talking a little bit about my career. This one slide just to show you, maybe as a motivation factor for the ones that are graduating this year, that you still have a lot of to achieve, and you will, and things will happen in your career. And I just wish the best for the group that I met here. Yes. Larissa?
Try clicking with the mouse just really quick.
Where?
The mouse on the
Mouse.
desk. All right. Now you can try the clicker.
Clicker.
Okay. All right. So this is the presentation outline, and so as I said, I'm going to talk briefly about a summary of my career from 2011 when I got my PhD at the UNL until this year, 2019. Then I'll talk a little bit about my research motivations and the studies that I do in Brazil. I'll talk about the laboratory that I work in the Federal University of Espirito Santo, some recent projects, and I brought some results from the projects that we are working on Brazil, because I think it's going to be very nice correlated with the things that I could do here as a visiting scholar. Then in the third part of the presentation, I'm going to talk about the current collaboration that was possible with Dr. Kim's infrastructure group and showing some results from the Slag characterization that was performed here, and about numerical modeling using the nonlinear viscoelastic cohesion model. And to the end, I'm going to give some acknowledgements. So about my career, my professional career, of course, started even before 2011 when I got my bachelor degree in civil engineering. I'm a civil engineer. But at UNL, I got my master's and PhD degree. My PhD degree was awarded in 2011, and it was under Dr. Kim, and I'm very proud to say that I was his first PhD student. And the title of my dissertation was Computational Micromechanics Modeling of Damage-Dependent Bituminous Composite based on the two-way multi-scale approach. You are very familiar with all those terms that is on my dissertation title, right? So in that same year, I got my position as assistant professor back in my country. So I returned to my country right after I finished my PhD, and I started to work at the Department of Civil Engineering in Brazil. And in 2011, I worked with undergraduate level course only. But in the next year, in 2012, I joined the group that worked in the civil engineering graduate program. So I could start doing research and having my first master's students. So I got 3 master's students when I started, and they all finished from 2012 to 2015. And I started to work with cement-based rheology at the beginning, with mastic rheology and asphalt mixture performance. Oh, and I forgot the most important thing from 2012, my first son was born, and in 2015, my daughter was born. So those are my biggest projects in life, and they should be here in my career as well. So I had my 3 first students, they defended, and we got all their studies published in good journal, so it was very nice. And then from 2016 to 2018, I had more 5 master's students, and they all finished on time, and we could work with different topics: numerical modeling, field evaluation, laboratory investigation, rheology, or mechanical performance of HMA. So it's a broad range of analysis that goes from laboratory experimentation, rheology, to field investigation, and of course, passing through numerical modeling as well. So in 2018 was the year that I came here to Nebraska, but I still had 2 students, still being advised by myself, and thanks to the technology, I continue to advise them even I was here, so they could finish their master thesis. And I also got the CNPq Research Scholarship in 2018. And then I got finally the Brazilian Federal Agency for Support and Evaluation of Graduate Education, CAPES, postdoctoral scholarship. So I got this scholarship approved, and then my department allowed me to come and spend this time here improving my education. As you know, professors, they are always learning, right? So that's why I'm here to continue my learning. And back home again, here I am in Nebraska. Just to situate yourself geographically, we are here, United States, and I put a snow symbol here to represent Nebraska, and you know why, right? We just had like a very strong winter. And Espirito Santo is here, so sunny in the southeast of Brazil, okay? So here is where I am working right now, the Federal University of Espirito Santo. Espirito Santo is the name of the state, and Vitória is the capital of Espirito Santo, is where I live in Brazil. So actually it's an island surrounded by the Bay Areas. The Federal University of Espirito Santo was founded in 1954, has a total of 4 campuses. In Vitória, there is the main campus, the campus Goiabeira, but there are 3 other campuses around the state. So the civil engineering department is located in the main campus, Goiabeiras. And I just put some pictures to show you the look of the university, the theater, the general view of the campus. And this is the building where the Department of Civil Engineering is located. And what are my research motivations? So you got a chance, many of you that are in this room, to watch Dr. Rezende's presentation and to mention how the conditions of Brazilian roadways are, and they are not in a good shape. Brazil has a total of 1.7 million kilometers of roadways. It's a really large country, but only 12% of the roadways are paved. So there are many still to be done in terms of constructing pavement structures. Most of the roadways are made of asphalt, so they are flexible pavements, right? So they are the constituents are asphalt binders and aggregates mainly. The latest report from the national agency showed that almost 50% of the roads are ranked as in terrible condition. Then to link as in terrible, they have many forms that they fill out, and they mention about the condition, the roughness index, the cracking, and the rutting on those segments that they evaluate to give the final report rank. So as you can see here, the conditions, more than 50 are either in bad or terrible conditions. So we can see a lot of fatigue cracking or permanent deformation. This is just an illustration of the damage. And we need to improve the pavements. And in our state, in our university, there was no professors taking care of the research line related to the pavement area. So in 2011 was when I was hired as a professor, along with my partner, Patricio Pires. It's a good collaborator on my projects, you see. But both of us, we started to work on the university in 2011. From that year on, we started doing research in pavements in our university, in the Federal University of Espirito Santo. Also, because of the geographic position, Vitória is located here at the coast. So there was this construction of the port of Tubarão in 1966 that was constructed to export iron ore to the world. And this port now it's the largest iron ore embarking port in the world. We have a lot of iron in the other states, in the nearby states. And because of the Vitória position, we had this port constructed that can ship iron ore through the world. And with that, ArcelorMittal, which is a steel company, decided to construct a branch in our state and taking advantage of the raw material that they need to make steel. So they have the iron ore available. So they start to construct this company, ArcelorMittal Tubarão, this branch of ArcelorMittal. Again, ArcelorMittal, it's a international company. So they built this company in Espirito Santo, and they are one of the largest steel exporters in the world. But because of that, we export a lot of steel, but we produce a lot of byproducts from the steel company. And one of the most known byproducts are the steel slags. So from the furnace, we have those molten, not good materials to be on the steel. So they are discarded. And when this material cools down, it becomes like a rock. And it's what we call the steel slag. And they need to find a use for this material. And they look for us at the university. So our research, I have a deep passion to study pavements, and now I start to have a deep passion to study a use for a material that is in my region, in my state, that needs a noble destination. So that's when we start to work with steel slag to give a noble destination for the byproduct of this huge industry that is located in our state. So they looked for us in the laboratory in UFES, so we start to put together this group of researchers, myself and Professor Patricio. So we start to get master's students to work with us on this subject. And since this first contact with ArcelorMittal and us for the projects, we start to develop many research about the use of slags, and we have so far investigating doing laboratory analysis, field evaluation, laboratory analysis for surface layer application, and also numerical modeling. All those big topics, they have slag involved somehow during the analysis, the analysis of the material. So what I brought to you today to talk, I will talk about two of the main applications that we look for of the slag. One of the applications is to use slag as an aggregate for asphalt mixture production. This project, we just finished one part last year when we are continuing to work on this same project, but doing a more deep evaluation. But basically, slag, the LD slag, there are several types of slag, but the LD slag has favorable frictional properties. It's a high hardness strength material, which is good for pavement and can resist to strip and rutting. However, one of the reasons that people in Brazil still think that they cannot use slag as a material for pavement construction is because the expansion of this material, if this material gets in contact with humidity and hot weather, heat. With heat and water, this material can expand. So they think that if we put this material as an aggregate in a pavement structure, we can develop internal stress that will trigger cracks on the pavement. They don't say that we cannot use slag, the Brazilian standards, but they say, okay, if you want to use, you have to cure this material before you use. Basically, put in water and make the material expand before it's used, and has to have a minimum level of expansion of 3%. But we start to think, is this 3% requirement for maximum expansion really required for use on HMA layer in the asphalt? This requirement was, when it was made, it was more thinking about the use of slag in base and sub-base, which is indeed in contact with water and not much with heat, but water, and the material can expand. But in the HMA layer, this material maybe it will be surrounded by asphalt binder, and the asphalt binder can protect the slag and avoid this expansion. That was our initial hypothesis. Why we evaluate if this slag will really expand when used as an aggregate for asphalt mixture production. So this study was published this year on the TRB. I can say that is in the initial part, still a lot to be investigated, but we published the results, and I'm going to show you in the next few slides about the results we got. Another study that we also have about the use of slag is the use of KR slags, another type of slag that does not have expansion at all. Actually, there is, but it's much less than LD. It's usually lower than 3%, so it's ready to be used in pavement. But it's like a new slag in our state, because the process to get KR slag was recently added to the steel company. So we investigate the use of this slag for soil stabilization, because this slag has major chemical components that make possible this material have some pozzolanic reactions as cement. So there are many references that talk about the use of slag already as a cement material. They call slag cement, actually. So this study was also published this year. We did a laboratory and field evaluation of KR slag as a soil stabilizer, but I'm not gonna go deeper on this subject because I will need another hour just to talk about this project. So I will talk about this one. And I'm very interested to talk about this other work that I do, which is related to numerical modeling, but still, I have still slag involved in this analysis. This is the student, Rodriguez, the first author of this paper, to try to evaluate what slag if I add slag in my mixture, how the characteristics of the mixture will change and we try to narrow down by evaluating the characteristics of our fine aggregate matrix to evaluate cracking, initiation, and propagation. So the question was, can LD2 slag be used as a filler in asphalt mixture? Does the type of filler, if I compare slag with hydrated lime, for example, which is a common filler in asphalt mixtures, influence the rate of crack propagation, initiation, and propagation? And if I go for numerical modeling to evaluate that, what are the required laboratory tests that needs to be done in order to get the input for the modeling part? And if I use numerical modeling, what are my limitations with the models that we propose? So going now for the results of the two projects that I brought that we do in Brazil that are very related to the test that I could do here in UNL. Let's talk about again about the projects that evaluates the effect of steel slag expansion. For that project, we took a sample of slags from the steel industry as is, without curing. This batch of slags that we brought has an initial level of expansion very high, 6.71. And we separated this big batch in 3 groups. So the first group we characterize as is, with no curing. And the second and third group we cure in laboratory to reach lower levels of expansion. And we also characterize those materials. The goal here was to see if, because of expansion, what's going to change in terms of material characteristics, mainly the materials that are required for pavement use. And in asphalt mixture, if I change the level of expansion, does it change something in my mix design? Do I need more binder, less binder? How about the performance of the mixture, the martial stability, the indirect tensile strength? What's going to happen if I have different level of expansions? Because if nothing happens, why do I need to cure? And cure takes time on the field, up to 6 months to reach the level that is required by the standards. So we took those 3 bags and we characterized common simple engineering tests that are required for pavement application. And I highlighted here mainly these absorption results, and you can see the slag as is has a lower level of absorption. All the 3 slags in the 3 levels, they had absorption values much higher than the natural aggregate. So what do you expect if you use an aggregate that has more absorption level than a natural aggregate in terms of mix design? You expect a higher consumption of binder. So we just stay with this information and let's see, this may affect our volumetrics. Also, the Los Angeles abrasion, it was much better than the natural aggregate because it was a much stronger material than the natural aggregate that we have in Brazil. We do have natural aggregates in other parts of the world that has better Los Angeles abrasion, but what we have now that are being used in the construction of our roadways are these natural aggregates with 41% Los Angeles abrasion, and slag is much strong material, which are much better Los Angeles abrasion. So this is also a good result for us. We also evaluate the chemical changes. When the level of expansions decrease, we can see that at the beginning, when the slag comes as is, you have a wide range of chemical components. And as we cure the material, looks like we have a stabilization of the chemical components presented on the slag. Going for the volumetrics, now we took 25% of the net. We did a mixed design with only natural aggregates. And then we took 25% of the natural aggregate and we replaced by slag. And the binder content didn't change. So our initial thought would be that we would require more binder. But since we only replaced 25%, it didn't affect the volumetric. This is very good because when you present this for the industry, for HMA plant production, they don't want to increase the binder content. And we can say, well, you can replace 25% and you still don't need to replace the binder content after mixture. But if you go for higher amount of replacement, we try with 50%, so the binder content increases. And the explanation for us was because LD has a higher absorption. So for higher level of replacements, you need more binder. But at a certain level, you still can get the same binder content. But even 5.9, there was no problem. It's not that much, let's say like that. It's still economically feasible. It's not a number like 8% binder. In terms of mechanical performance, as I cured the slag, nothing happened with the Marshall stability. We still got the same results. And even with 50%, I still have the same Marshall stability. It didn't decrease, but it didn't increase also. We were expecting, since it's a more strength, that has a higher strength material, we could get an increase on this value. But again, it was 25% of replacement. So it did not change. But again, expansion didn't play anything on this parameter. So it was not a problem to use slag as is with higher level of expansion. And from the indirect tensile strength, we also see that there is no variation, no decrease compared to the natural aggregate. And I increase with 50% on the indirect tensile strength. And this result call our attention, and we just think, wow, if I replace natural aggregate by slag in higher amounts, I increase the indirect tensile strength. Why that happened? Better adhesion? So there are some papers that are trying to investigate adhesion between slag and asphalt binder. Or because I use more binder, it could also be that reason. So there is a need for a better assessment on mechanical and chemical addition. And I leave this question now because this question will be answered with the results that I got from UNL, with UNL collaboration. So, changing subject again. That was about the slag projects regarding the effect of expansion. But we also did some numerical simulations to see the effect of slag regarding the cracking development, initiation and propagation in the fine aggregate mixture. So Rodriguez, my master's student that finished last year, she did a numerical analysis of the effect of slag as a filler, and she compared the results with a same mixture but using hydrated lime as a filler to see the effect of slag in the modeling parameters. So she did a DSR test to obtain linear viscoelastic properties. She did SCB test to do an experimental numerical calibration procedure and get the nonlinear viscoelastic cohesion damage parameters. And with the parameters, nonlinear viscoelastic cohesion parameters and linear viscoelastic parameters, she could use those as an input to validate in another test, the mixture performance. The model that she used is the nonlinear viscoelastic cohesion model proposed by Allen. And that is, in this model, it considers the traction separation curve in the cohesive zone a nonlinear, as you can see here. That's why the model is called nonlinear viscoelastic, has viscoelasticity included. And the model is extrinsic because the cohesive zone just started after a certain level of stress, does not start from zero. So she did the DSR test, got the linear viscoelastic properties. Then she did SCB test, where she allowed cohesive zones being developed throughout the sample. And she played with the parameters until she got a nice correlation between experimental and numerical results. That's what we call a calibration process. And from that, you can see here experimental results in black and numerical results are the colored lines. You can see here comparing slags and the fine aggregate matrix with slag and fine aggregate matrix with hydrated lime. there are some changes in the modeling parameters. So these students, she did a parametric analysis of the effect of each parameter. I'm not going to talk about this parametric analysis, but I'm going to highlight here the change that she observed. For the fan mixture that used slag, the delta value was higher than the delta value for the mixture that used hydrated lime. This, from her parametric analysis, is an indicator that slag may produce a more ductile material. So we have an increase on the area under the curve, so it makes the material more ductile. She also observed that the M value decreased with slag 0.8, with hydrated lime is 0.73. That means that the damage propagates slowly on the fan with slag in comparison with the fan with hydrated lime. And finally, she saw that the stress initiation criterion is lower for the slag in comparison with hydrated lime. And this may represent the material behavior slag reduced the brittle fracture behavior. So the brighter the material, we expect higher level of stress initiation criteria. So slag, it was less brittle, and it also corroborates with the delta value. It's more ductile, and we have cohesive zones developed earlier in the mixtures with slag. So she took the parameters from calibration and she used as input to simulate an IDT test to validate. Then we observed that the initial slope of the curve, force times versus time, the initial slopes were very well determined, and you can see a good match between experimental and numerical. And the mode 1 stress initiation criteria was satisfactory because it also impacts this initial slope. But we didn't have a very good match and the post-peak after the peak load. So this may be due to some mode 2 fracture that's happened, because when we do a calibration, we calibrate mode 1 parameters, but we still need to find mode 2 parameters. And we didn't consider, but the test that we use, the IDT, it's different from the SCB with a notch, which is considered pure mode 1. IDT may also have some mode 2 cracks being developed, and maybe if you calibrate or find a way also to get mode 2 parameters, we can get better match after we have several cracks being developed. So the mode 1 nonlinear viscoelastic cohesive zone parameters from the integrated numerical experimental approach seems to be well established. The results are fairly comparable between numerical and experimental analysis. The parameters could be validated, consider different test modes. So we did got the parameters from SCB and we validated with a different test mode, which was good. But it's still one question remaining. We did this validation considering one testing rate. But what if we change the testing rate? Can we still use the same parameters? So we still need to go further on this investigation to evaluate different rates. Or if we have aging, what happens with those parameters? So those are all questions remaining that we continue to research on. So with those two results in mind, I hope you still have in mind, it's a lot of information, but they are well linked with things that I did here. I came to Nebraska, April 2018. So those results that I presented, they were just, I just finished in Brazil and then I came for this appointment as a visiting scholar. And what I was hoping to get here was knowledge. And how we get knowledge? We need books, we need fundamentals, right? And I had Dr. Kim, which is, has a lot of expertise and fundamentals in his mind. So we could meet and talk and I get more fundamentals from him. We also get knowledge with people, and by get together with this group of students, PhD students from Dr. Kim's group, I also got many knowledge, believe me, from each of you guys that are here. And also to get knowledge, we need technology. And we also had good technology here with the Nano Center, with the laboratories that are under Dr. Kim's supervision. So I had everything that I was dreaming of as a researcher. Good people with good knowledge and background, fundamentals and technology. So I can right now say that I could see that would be a nice experience for the postdoctoral program. So I brought with me some slags from Brazil. I knew that I was coming here and I had access to nice equipment and we could talk. So I brought some piece of these steel stones, steel slag aggregates, and I start to do characterization of the slag with some tests that I could not do in Brazil in my laboratory. So with the collaboration of one of the students from Dr. Kim's group, Mrs. Kamadit, we did some roughness analysis based on the laser scanning microscopy, and also elastic modulus evaluation based on nano-indentation tests. So we took samples, we polished, we grounded the material, and we did this test for nano-indentation, and we also did this evaluation with the microscopy to get the parameters and try to correlate with the unknown questions that we had from the projects in Brazil. So from the nano-indentation results, what I could think, and again, it's still thinking, it's a never-ending process, but what my initial thought was, from the nano-indentation test, we can see this is natural aggregate and seems pretty homogeneous when you look using the nano-indentation equipment. This was expected, as Madia told me, for natural aggregates, pretty homogeneous, but she was surprised when we put the first sample of slag and we saw heterogeneities throughout the analyzed area. And this heterogeneity seems to decrease as the slag is cured, at least from this parameter point of view, from the elastic modulus. So we had, with no curing, the higher level of expansion, elastic modulus here is the gray line here, has a range, a broader range, but the average seems to be around 130 gigapascal. And as I cure the slag, this broader range starts to be narrowing down, so less standard deviation among the results. But even with this variation, the average seems to be quite similar between the three slags. So I just compare with the chemical results that I had from Brazil from X-ray diffraction. And we also observed from the X-ray that we had many chemical components for the high level of expansion. And after curing, we have kind of a stabilization of the chemical components. So the results match it. But I was still interested in, okay, how this will affect the mechanical performance of my mixtures then. I have the answer why it varies, maybe because of the chemical chains, but how this could affect the asphalt mixture performance. That's my main question as a civil engineer. I want to use the material and how this can affect. So we saw that in general, the elastic modulus with the level expansion, the average didn't change much. And comparing with the natural aggregate, it increased. Natural aggregate, the average is around 90 gigapascal and slags around 130. So it's a little bit higher. But this difference, maybe it's not that considerable when you think about the mechanical performance of your asphalt concrete. And maybe that's why we didn't have much change here. The elastic modulus, indeed, it changed, it increased a little bit, but this increase was not significant when we added this material in 25 and 50% on the Marshall stability. So from the XRD, the change on the chemical components show the change in chemical components due to hydration process. The nano-indentation show a more homogeneous material elastic modulus when we had cured slags with level of expansion lower than 3. but not much change in the average elastic modulus. So comparing the nano-indentation results with the macro scale results, they kind of cooperate with each other with no significant change on the Marshall stability here, because we didn't have much significant change in terms of the average elastic modulus. Now going to the analysis of the roughness by using the laser scanning, you can see here the natural aggregate has a higher roughness than the slags in general, and the level of expansion again didn't vary much the roughness. But one thing was interesting. The higher the roughness, people say, the better the mechanical adhesion between binder and aggregate. But why, when I have more slags, I have a higher indirect tensile strength? Indirect tensile strength is an indirect way to measure how these components are working together in terms of adhesion. But the roughness of the natural aggregate is higher. So why that happened? I was expecting lower roughness for the natural aggregate, higher for the slag. Then I could say, oh, that's why slag has better performance, because higher roughness, better bonding between binder and aggregate. So maybe the chemical characteristics, not roughness, but the chemical characteristics that gives the chemical adhesion, it's more significant than the physical, the mechanical adhesion. So from this study from Caro and Rojas from 2019, they show that there are some chemical components that they are really important when you want to have a better bonding between aggregate and binder. And seems like silica is the component that plays a role negatively in terms of adhesion, and oxyl, aluminum, iron, magnesium have positive effects on the adhesion. So I went to my chemical results again, and what I observed was that my slag has a lot of those good components, good oxides. Calcium 43%, silica 12%, aluminum, magnesium 5%. And also have silica is negative, but it still have 12%. But my natural aggregate, it was a granite, which is rich on silica, that brings the negative effect. So now it starts to make sense. So I took another slag that I had that is rich on silica to see that if comparing two different slags, but one that's rich on this component would have negative adhesion. So we call DP slag, dry peat, has 32% of silica, so much higher than the LD, and other components more or less the same, and less iron, so would be even more negative in terms of adhesion. This slag, it was the one that has the highest roughness, and if you just analyze roughness and you believe that the higher the roughness, the better the adhesion, you may be having results that you're not expecting in terms of mechanical performance. And then from the simple boiling test, this slag performance the worst compared with LD. This picture you cannot see very nicely, but it was clear that the DP slag and LD with the same binder content passing through this test here, the simplest test that people do to evaluate adhesion between aggregate and binder. This DP didn't have all the particle cover by binder. Binder didn't attach to this material. So that's how those results that I got from here, they could be well correlated from the things that I still was questioning myself back in Brazil with my projects. Was very interesting, and we are still working on the analysis of those. And going now to the numerical analysis, it was another topic that I work heavily here, in US during my visiting appointment, you know that to model cracks, we use the so-called cohesive zone models, right? And the main difference about the available cohesive zone models in the literature are, the main difference are in the initial slope and the shape of the curve after peak. So many studies use the bilinear model, it's the simplest model. It considers a linear decay after peak, and the initial slope starts from 0. So this model is called intrinsic because it starts from 0. And there are many, many studies that use this because it's the simplest and easy to be characterized in laboratory and has 2 main parameters. But there are other models that is still intrinsic, it starts from 0, but has a nonlinear decay. So I just put here 2 Edelman model that has exponential decay. There is the extrinsic models that does not start from 0, starts from a certain level of stress, and they decay. This one decay linearly, so it's the model proposed by Camacho and Ortiz. And we have the Allen and Searcy model, which is the nonlinear, is a extrinsic, does not start from 0, and has a nonlinear decay. We believe this model is more suitable for asphalt mixture prediction because it accounts for the viscoelastic behavior of asphalt materials by including the convolution integral in the model. But in order to use this model, we have to define an internal state variable that we're gonna dictate how damage propagates when cracks start. And this internal state variable can be different functions. Allen and Searcy proposed a phenomenological law, damage law, that considers 2 parameters, A and M, to mention how the damage will propagate throughout the sample. But we also have another model proposed by Young and Allen, 1990, has a more theoretical framework, and I'm not gonna go details about how they developed this equation, but there is the paper with all details. And there is this model that is proposed by Souza. It's based on a Gaussian damage law, which has this mathematical description. Remember from the study that I presented from my student in Brazil, she validated the FAM prediction by obtaining properties from laboratory and then simulating another test, but she did just for 1 rate, and she used this model here for the internal state variable. So I need to verify, what if I change rate? Can I still use this model? So to verify that, we start by looking one study from Kim and Aragon, published in 2013, where they had the fine aggregate matrix behavior in different rates. So this is laboratory data available for us, anyone can use. And they had the linear viscoelastic properties there. So I could use that to verify if the model that I'm proposing as the best one to predict crack initiation propagation in asphalt, it's suitable as a rate-dependent model. So I simulate the same test that the authors did here. I input the linear viscoelastic property that was available from this reference. And basically the geometry of the beam was 150 by 75 high and thickness 25, had a notch length of 25 millimeter, and they tested 3 different rates. So what I did was I took these tests and I calibrate for 1 rate, 50 millimeter per minute. Then I used the same parameters to predict the behavior in 2 other rates. And that was the result. So as you can see, for 50 millimeter, the curves from numerical and experimental, they match, but of course they match. I calibrated with 50 millimeter, okay? But then if I use the same parameters for other rates, I had this prediction the green here and the orange here, that does not match with the green curve from the experiment and the orange curve from the experiment in other rates. In order to use this damage evolution law here, we need to recalibrate every time that the rate changes, and we don't want that. We don't want a new test every time we change rates. And in pavement, we don't know the actual rate that is the pavement is subject to. We want a model that takes care of the rate dependency of the material. So I try to investigate other models available of damage propagation rate. And by looking at this model that is based on a Gaussian function, you can see the mathematical description of this model. It's similar to the mathematical description of a Gaussian function because it was made based on this assumption that the material follows a Gaussian function. So the shape of the model has the shape of a Gaussian distribution function. So I try to use this model that uses this internal state variable. To use this model, we need two parameters, this big delta and the lambda bar. But lambda bar is not a value that we need to calibrate. It comes from an experiment, because if you plot the Gaussian function, the lambda bar will be the position of the mean value. So it comes directly from the experiment. Also, the big delta does not need to be calibrated. It's basically the standard deviation of the values throughout the X values. So I try to verify if this model based on a Gaussian function could work for our asphalt materials prediction. So first we need to determine our damage function. So here damage was defined as the difference between the non-damage to the damage testing results. Okay, so here I have the experimental results from a SCB with damage, but I didn't have a test result for the non-damage case. For the non-damage, I basically simulate the same test, but I didn't allow cracks to be inserted. So I would have my non-damage curve. So I calculate the alpha as a function of time, and we got this curve. So basically alpha goes from 0 to 1, and 1 is when we have completely separation. And we calculate alpha dot, the rate of damage propagation. And you can see the shape of the curves. It follows, not perfectly because this is experiment, but it follows a Gaussian distribution. And it's independent of the rates. The two parameters that are required for the Gaussian distribution function is the position of the mean value and the standard deviation. Even if I change the rate, the peak position is the same. So it's rate independent. And delta value, this big delta, is the standard deviation of the values found throughout the analysis data. So conceptually, this model may work based on this analysis. So I tried to validate. So we went for validation. So I took one test data from that paper that I use as a reference, which I took the data from with a loading rate of 10 millimeter per minute. And I used the delta value that was obtained from the analysis of the experimental data. And I also took the data from the big delta from the experimental data. But I saw that this value also needs another calibration. So I calibrate the big delta, the lambda, I use the same based on experimental evaluation. And I calibrate the results, and you can see from the contour plots that the crack path actually follows what we observe in the laboratory. And I took now this curve here, the parameters that were valid to fit the experimental data with numerical data, and I tried to predict the behavior in different rates. And that's what we got. And I apologize here, the curve seems the same, but in my laptop, I have dashed lines for numerical and full lines for experiment. But I think you can understand that the results they are amazing, right? So the same parameters that I calibrated for one rate, I could predict the behavior of the sample in different rates. So now we're talking about a rate-dependent model with an internal state variable that accounts for the rate dependency of asphalt materials. But one sample, one material is not enough. Let's see if this works with a different type of sample. My friend Laura, she had a test done here in UNL. So with a fan that was obtained from an open graded friction coarse mixture, totally different mixture composition than the previous one. So, and she did two tests, SCB test and beam tests, okay? So here are the geometries that she used for SCB, 150 millimeter diameter with 75 radius and 25 millimeter thickness. And the beam sample was 150 millimeter length, height 75 with 35 millimeter thickness. Both samples have a 50 millimeter notch length, right? And she tested the SCB in 3 rates, and she tested the beam in 1 rate. She also obtained her linear viscoelastic properties from DSR frequency sweep test. And we took this data, and Gabrielle Nisan-Guilluman helped us here with the laboratory test. So it's also a collaborator on this part of the test. And we calibrate her test from the SCB that we use for calibration. That's our approach to use this model. Take an SCB test and calibrate for 1 rate. So we calibrate for 0.5 millimeter, and we predict for the 5 and 10 millimeter rates, different rates. And I also try to predict the beam behavior. So here it is. Now it has difference between numerical and experimental. Good. So we calibrated the 0.5 millimeter is the dashed lines. And I just put 2 results here from the experimental data that Laura has, but Laura did 5 rep plates from each rate. And I just took the minimal and maximum and put here just to show, because we have variability in laboratory as well. So we calibrate for the 0.5, and we use the same parameters to predict the behavior in other rates. And that's what we got. And that's what we got visually in the contour plot. So here is a movie.
Abuse user.
Yeah. So you can see we apply the load here at the center middle point. So we have tensile strength concentration here close to the notch tip, and compressive stress concentration here where the load is applied. And after a certain level of tensile strength, we have cracks start to be developed and being propagated throughout the sample. So that's what we predicted numerically. And the same behavior that we obtained numerically was also observed in the experiment. Then we took the same parameters that we calibrated for one geometry, and we tried to see, can I use the same parameters if I change the test geometry? And we also got a fair prediction of the 3-point bending beam test with the same parameters. So the nonlinear viscoelastic parameters were geometry independent. So are we talking about now about a material property? It's not a parameter anymore. It's not geometry dependent. So that is one thing that we got, and we're still working on the analysis of this data. I brought to you to show those interesting results. And again, the contour plots, they seems quite reasonable. The way that where the crack starts and how it propagates, it's reasonable with what we observed in the laboratory. This one is going slowly. So let me just move forward. So you can see this test is done in 0.5 millimeter per minute. It's really slow test, but you can see crack propagating at the center as we expect. So those are the results that I could get. So basically I had one question in mind when I came from Brazil. Can I use the nonlinear viscoelastic cohesion model? And which internal state variable should I use in order to account for the rate dependence of the material? And we could actually, we change the way we approach the model, because we verify that the phenomenological law that people that use the nonlinear viscoelastic cohesion model usually use is not enough to account for the rate dependence of the materials. By going through a Gaussian distribution function, now the model can account for the rate dependence of the material. So with that, I end my talk here, and I just put together everything that I could accomplish throughout this whole experience. And this does not involve not only the things that we can write and publish paper, but we can accomplish much more, which is this relationship, multicultural learning with people from different countries, different cultures. I could go for conference. I attend 3 conferences throughout this year. Group meetings every Friday, very fruitful discussions with things that I never thought that I could heard about. Lunar soil, for example, was one thing that is in my mind. Bond modeling. Asphalt is the one that I'm used to, but I could learn so many things with the group meetings. Partnerships with other professors and researchers that we will continue to work with. And personal achievement, my first half marathon in Lincoln. I could run my first half marathon, and it was in Lincoln. And my son and my daughter had a wonderful experience this year. So with that, I end my talk. Thank you.
All right.